Next 1.5 hours, I'm going to talk about the Intel tools available on Aurora. So there are many tools. So we have APS, VTune Advisor, and xpu-smi, and unitrace. So I will give you overview of those tools, and then we will have a quick demo. Even though the Aurora is under maintenance now, but I have some pre-collected data. So for the post-processing process, we can do some demo depending on time you have. So the today's talk is has a two part. The first part is Intel analyzers on Aurora. So Intel analyzer is embedded into the one API module, so you don't have to load any tools. So you can just use whenever you have one API module, you can use those tools. So Intel VTune APS, those are popular tools from Intel, and Intel also Advisor is also part of the analyzer. And then I'm going to talk about the lightweight tool from Intel. They are not included in the one API module, so you have to load additional modules. So I will talk about that. So unitrace is a simple tracing tool, which is very similar to iProp, but this is kind of Intel version. And then xpu-smi is somewhat similar to NVIDIA SMI from NVIDIA side, so you can monitor your hardware utilization using SPSMI in real time. So that's the overall agenda. And also, if you have any question, please unmute yourself and then ask question during my talk. We can discuss it, okay? Okay, Intel Analyzer. So this part, I will give you some overview of Intel VTune Profiler and some capability, and then I will show you how to run it. And I mean, not showing, but I will tell you how to run it once system is back. So how to configure VTune, some different CPU, GPU analysis types, and some controlling collection overhead, and how to visualize your result. And then I will talk about advisor overview, how to configure advisor on Aurora, and um, uh, the one of popular feature of advisor is GPU loop analysis. So I will give you some cases with GPU offload analysis. Okay, so let's start with the VTune profiler. So VTune is one of the popular profiler available in VTune and Intel. So I mean, right ago when we just used CPU, VTune was one of the favorite profiler on the CPU side, right? So now Intel provide additional accelerators, so they extended the VTune profilers to many different architectures. So you can use VTune to get the data to find out the bottlenecks of your application on the system. So it is a suite of the profiling for CPU, GPU, NPU, and memory hierarchy, cache and storage and offload and depth and power consumption, etc. Right? So you can you can get the data for the application, or you can also get the system-wide analysis on the node level analysis and system level analysis. It's available. It supports SQL, C, C++, Fortran, Python, Java, and the mixture of them. It's available Linux, Windows, etc., and also supported in the containers and the virtual machines. So you can analyze data. So you can collect data, hardware, software sampling, tracing without recompilation. So the default mode is kernel level analysis. So usually your application uh, so usually you want to understand your kernel performance, kernel-based performance. You don't have to recompile your application. You can just run it with VTune, and you can collect the corresponding data from hardware and software. And you can also see some more detailed data on the source line. In that case, you will need to include the debug symbol, and then you may need to recompile your application with debug symbol. But there is a more deeper analysis. And also you can get some architecture diagram and histogram and the timeline view. And depending on the cases, you can filter or you can organize the data to find your answer. So the goal is not running VTune, right? Goal of running VTune is after running the VTune, you want to understand what's wrong, what's slow, what is low-hanging fruit, and then you need to tackle that part and then get better performance. That is goal, right? So for that, filtering organized data is pretty important. Intel provide that feature as well. And you can also use it in your way, so user interface through the user interface or command line, or profile locally and remotely. So on right hand side, there is a couple of snapshots to show the features. So on the top, it provides what kind of analysis is available, right? So for algorithm, parallelism, accelerator, microarchitecture, and I/O and platform analysis, there are several different collection mode here. And the screenshot shows what kind of source line view you can expect, right? So in this case, the source line 158, 59, 60, it is showing some instruction count, and then you can check whether your high level language is correctly interpreted through the assembly, so you can see how many instructions executed, right? So there's kind of very low level view. And at the bottom, it provides some architecture viewpoint of the analysis. So it provides what kind of component you have. So this is on GPU side. You can see there is some sub-slices and then some sampler L1, L2 cache and L3 cache and GTI and etc. Right? So you can also see the hierarchical view and then what kind of how much utilization happen per component and then how much bandwidth you can get from the device. So this is kind of a quick overview. And again, VTune has a lot of features for profiling. So the first thing is the algorithm optimization. So for that, you can do the hotspot analysis, anomaly detection, and memory consumption. So this is kind of extended version of this slot. So and we can also do some microarchitecture exploration and memory access pattern analysis. So you can find out which component is your performance bottleneck. For example, which pipeline of your execution unit is bottleneck or memory hierarchy, which level memory hierarchy is performance bottleneck. So you can identify that mostly on CPU side. And also Intel provide the accelerator. So except for the accelerator, it gave us three options. First one is GPU offload analysis to identify how much offloading tax we are using, we are paying, right? So data transfer cost, etc. And GPU compute media hotspot is more deeper dive analysis on the GPU kernel analysis. So it provides some hardware sampling data, software sample tracing data, and then provide um, a lot of information, utilizations, and then memory, the bandwidth, etc. Right? And then CPU FPGA interaction mode is also under collection. For the parallelism, you can also get the thread information, and also you can do the HPC performance characterization. HPC performance characterization provides host and accelerator data, so it is also popular to identify some issues on the GPU uploaded data, the applications. And platform analysis for input-output system overview and multi-node analysis. VTune has some application performance snapshot view. They have some independent executable APS. So VTune is really good at the on node level analysis, on the device level analysis, but sometimes it collect too much data to be done at scale. So Intel understand that is kind of the issue at scale. So and again, Aurora has a lot of different nodes, a lot of nodes, right? More than 10,000 nodes and more than 60,000 GPUs. So definitely running VTune at that level is not viable option. So Intel has developed another tool called APS Application Performance Snapshot. In this case, they picked up some set of the subset of the counter data and then reduce the overhead, so users can run the APS tool at scale. So recently they demonstrated using the APS, they could collect the performance data with more than 2,500 nodes, which is a quarter of Aurora size. So in that case, the tool works pretty well. So APS could be a good starting point to understand your performance characteristic at scale on Aurora. Anyway, so how to configure the feature in Aurora? So again, the Intel Analyzer, including VTune, is embedded into the one API module, so you don't have to do anything actually. once you log in or once you get the compute node through the scheduler, your one API module is already loaded. So current default one API module is 25.0.5 version. So in this module, you can see the VTune version 25.0.1 version. So this is what you're using. Depending on some situation, sometimes you have a newer version of the VTune. In that case, we can provide a newer version of VTune out of this module. So you can also use that. So again, with a couple of slides, I showed a lot of different features of the VTune. So the easiest way to get what kind of the features are available is just VTune Health, right? VTune Health Collect. You can see all different types of collection mode is available. And if you want to see more detailed the analysis type available now for analysis type, you can do the VTune collect GPU hotspot. So simply, I have a Aurora node here. So not Aurora node, but a login node. So on login node, even though we cannot run the VTune, but at least you can see the features, right? So if I just log into the login node, you can see we have one API release 25.0.2 version. And if you do the VTune help collect, it shows all different uh, collection mode, right? Performance snapshot, hotspot, anomaly detection, etc. This is what I explained at the previous slide, right? And if you're interested in VTune GPU hotspot analysis, you can then collect GPU hotspots. And then it will give you all the additional knobs available for the GPU hotspot analysis here, right? So this is my favorite way to know, check what kind of the VTune features are available for my testing. So anyway, yeah. And then the first knob you may try out is performance snapshot analysis. So this is, again, as you can see here, VTune has a lot of different collection mode here, right? So it's very easy to lose the way where to go, right? So because of that, the VTune Intel suggests to run this analysis at the beginning. So what you can do is you can run your application with the VTune collect performance snapshot and then using your application. So what it's doing is it just run your application with the minimum set of the data. And then it will give, once you're done, it will give you how much time spent, what is local core utilization, what is microarchitecture usage, depending on retiring, front-end bound, bad speculation, back-end bound, memory bound, core bound, etc. Right? And also memory bound, how much pipeline used, and then factorization. So after collecting the minimum set of the the data, it provide, oh, based on this performance snapshot analysis, you may try this collection as a second step. So since in this example, it has pretty low threading and low utilization, core utilization. So performance snapshot suggests, oh, you may try out the hotspot analysis to see the more deeper diving understanding on the for the kernel level analysis, or the threading analysis, HPC performance characterization, or microarchitecture exploration, or memory access pattern because based on the this analysis, right? So this is kind of a suggested way, but but some case if you have a application fully offloaded to GPU, right? That means you run just to use the GPU, and that means your CPU cores are idle. So in that situation, this suggestion maybe give you a wrong direction because it just say, oh, you don't use CPU, just do the more work on CPU, but it's not useful, right? So it's up to you, but as always, you need to you can get some performance hint from your profiler, but you need to think about what it means and whether this is a valid one or not, right? So, yeah. And the next one is application performance snapshot. It's kind of a confusing name because previous one is performance snapshot analysis, and now they're saying application performance snapshot. But this APS is also one of my favorite one to start because when you run the Aurora, probably your application is running. At least you finish the debugging, right? So and then by the design, recommend our users to use a big portion of Aurora file, for example, 10%, 20% of Aurora running, right? So because we are ALCF. So if so, probably you ran your application with some real workload and Aurora maybe 1000 node case, for example. And then you may be curious about how good my application performance is on Aurora, right? So at that level, you're already running a scale. Attaching VTune could be too expensive. So in that case, my recommended way is running your application with the APS, which called application performance snapshot, and see the overall characterization of characteristic of your applications, right? So how to run APS is just like MPI run and ppn, GPU type compact as usual. And then before your application, just add APS dash all and then APS result directory. So just name APS result whatever, right? So we have some example at the end at the demo, so you can see what you can see the details. But anyway, so you just run it with APS and then run your application again, right? Maybe 10,000 node case. And once it is completed on the login node, you can just do the APS report and APS result directory, and then you can generate some HTML report. It also has some raw data through the command line. So once you get the HTML report, you can download HTML to your local the desktop or platform, and then you can open it up, and then you can see this kind of the yeah nice HTML file. So it will give you application name, when it run, and how many MPI rank, CPU time, GPU accumulated time, and IPC instruction per clock cycle, and then the polling prop rates on CPU side and the CPU gigahertz, GPU utilization, vectorization, MPI time, IO time, and etc. Right? So you can see high level MPI time and some GPU stabilization, physical core utilization, memory store. So from this example, you may see, oh, my application is using more MPI time than expected, or my application is a pretty low GPU utilization, or my application uses very high memory store. So you may have some experience on other system, and then you may have some idea about your application characteristic, and then you may think, oh, this is unusually long MPI time, or this is unusually low GPU utilization, GPU unusually high store ratio, and then that could be your next point to tackle, right? So and then you can run HPC performance analysis for the deep dive on the MPI activity authorization or GPU analysis to understand GPU underutilization. So there is kind of a scale, and then you can think about what could be the next step on the analysis. And then another characteristic is HPC performance analysis. So you can analyze your compute intense application with this performance HPC performance analysis because it provides physical core utilization, vector engine utilization, and memory bound vectorization, and also some OpenMP offload or SQL compute task. So this is kind of snapshot. You can see the CPU activity, GPU activity, and also platform diagram. On the Aurora, we have two Xeon processors. You can see the traffic between the two Xeon processors through the UPI and HBM bandwidth on the CPU side and DRAM bandwidth on CPU side on each core, right? And then it also provides the GPU utilization and it's busy and also hot top corners from of the GPU upload code and secret code. So so this is kind of usually the useful next step from the APS analysis. And in order to run this HPC performance analysis, you need to use VTune. So like you did on APS, MPI and PPN, and then the VTune collect HPC performance, and then you specify the result directory. So this command line, you don't need to remember that. I have a cheat sheet at the end of this slide, so you can use all the command line available. So you can use that as well. So yeah, this is kind of a next step after APS analysis. And then the another useful feature is the GPU offload analysis. So this is to identify whether application is a CPU or GPU bound. And also you can also see the detailed breakdown for different host device operation for each GPU and compute task. So how much time used by allocation, how much time used by host to device to data transfer, device to host to data transfer, how much execution time on the GPU, specific GPU, and how many synchronization happens. So on the right hand side, you can see 6 GPU devices available on Aurora, right? And then each device has two stacks, stack 0, stack 1. If you extend it, you can see the kernel executed on the GPU stack 1, and you can see here host to device transfer time is pretty small and execution time is here, but the device host time is pretty long. So this is kind of a very simple benchmark. It's not, it's unusual characteristic, but at least from these pictures, you can see how much time used by the host data device data transfer and how much execution time is used, right? And also on the timeline view, you can see the correlation between the CPU host and GPU activity, and also you can see host device compute and memory activity. For example, GPU memory access and system memory access, host to GPU memory access, and stack to stack access, and PCIe bandwidth. Here you can see at the very first tab is different characteristic, and then for each component you have a 6 GPU mode, right? And then you can see timeline view here, the green part and the yellow part, and or sometimes it's kind of the line plots, right? So using this one, you can see over time what kind of activity happen on CPU side and GPU side. So this is HPC performance analysis and GPU offload analysis is mostly about provide both of GPU and CPU activity. GPU offload analysis provide more details about the transfer between the CPU GPU. So this is very useful to understand whether you are using the CPU and GPU together well or not, right? And then you may realize, okay, the GPU upload traffic is good enough. Then you can see, now I just want to know how much time is used by the GPU kernel itself, right? And then more detailed understand information. So for this aspect, you can use GPU compute hotspot analysis. So it provide more GPU kernel information with high GPU utilization. And also you can identify what is possible reason for store or low occupancy or options. And you can also explore performance of your application per selected GPU metric over time, and also analyze what is a hotspot of hot kernels for inefficient kernel code algorithm and incorrect work item configuration. So on the right hand side, you can see overview of how much utilization happen on GPU side, how much occupancy happen, and what is the hotspot, etc. Right? So to run GPU compute analysis, it's simple. So you can just use the VTune, collect GPU hotspot, and then put the result folder name, and then you can just run your application. So GPU hotspot analysis provides several different viewpoints. So first one is memory hierarchy diagram here. So here you can understand GPU architecture. For example, in this example, you can see the Xe core. This is the main engine of the GPU execution. Inside of the Xe core, you can also see different components, the vector engine and thread dispatcher, and also SLM, LSC, right? And then also L3 cache shared by the different Xe cores, and then the HBM shared by per tile, right? And then PCIe and then less replication CPU side. So from this hierarchical architecture viewpoint, hierarchy diagram, you can understand which components are utilized, active, or how much bandwidth happen between the different cache hierarchy. You can understand that information. So and also we can identify the memory cache unit, the code extreme bottleneck, or you can make decision, data access patterns in your algorithm is good enough or not, right? So this is one feature of the GPU hotspot analysis. And then if you use the platform view, you can also observe correlation between the host and device metric like a GPU offload analysis. But the difference is GPU offload analysis platform view provide more details about host device activity, but the GPU hotspot analysis platform view provide more detailed activity on the GPU side. For example, GPU vector engine utilization, compute thread dispatch, XP pipeline instruction, GPU visual frequency, and also GPU memory access, S3 cache bandwidth and misses, right? So again, the configuration is same. So at the very first tab, you can see different component of interest, right? And then each component, you can see different GPU devices. And then you can see all the features here, right? So if you just put on your cursor on top of the timeline view, it just grab the text view. So at this time point, GPU 5 has XP send instruction this many, and the control instruction this many, and some ALU 012 instruction is this many, right? So this kind of detailed information you can get from GPU hotspot analysis platform view. Okay, and then um, so from GPU hotspot analysis, you can identify what is the hot corner. For example, I'm running some CFD applications on Aurora node, right? So I'm running CFD application for maybe an hour. And then you want to know, okay, which kernel spend most of time. So you understand your code very well. Probably you have you're understanding which code, which kernel is kind of the hot kernel, right? And then you run VTune has GPU hotspot analysis and you get the information. So probably you see, oh, I see this smooth kernel spend most of time. This makes sense because in other platform also smooth kernel spend most of time. But for some reason, the computing reaction kernel spend 20% of time. This is a nonsense because in other platform, when I run the same workload, this reaction call, computing reaction part just spend less than 5% of the entire application time. But in this platform, for some reason, it spend more than 20% of time. So that could be starting point of profiling deeper, right? So now you identify which kernel you need to go into, right? So for this specific kernel, you may want to see, okay, now I identify what is kind of the possibly problematic kernel, and then you want to see what happened inside the kernel. So for that level, kernel-based analysis is not useful anymore. You need to go deeper than that, right? So for that aspect, we can provide the source level in kernel profiling. So at this level, we have to link your source code to the metrics. So if you need to provide more information, debug information. So you need to build your application with the dash additional flag, dash debug info for profiling and dash G line table only. So these two flag is a lightweight version of the debug symbol. So you can simply put the dash G and dash O3 and run build again, but the dash G has a lot of information required by the debugger, but profilers don't use all the information. So if you want to reduce some overhead using the dash G debug symbol, you can just use these two flag instead of dash G and build your application again and run it with VTune source level analysis. So this is the instruction count analysis. So how to run VTune collect GPU spot and then add additional NOP characterization mode instruction count, then run it again, right? So if you do that, it will count all the execution frequency of specific classes of instruction. For example, control flow instruction, send instruction, single precision instruction, double precision instruction, and other instruction. And also it gives you efficiency of SIMD utilization by each kernel and then some extra additional information. On the right hand side, you can see the collected data here. So in this example, oh, this line spanned this much of send instruction, this much of single instruction, this much double print instruction, this is other, something like that, right? So you may find out per each line how many instructions are executed, and then in general, if you write it down, this is high level language, you expect that is correctly interpreted by the compiler and then generate the optimal assembly. Yeah, mostly yes, but in some cases no. So in that case, even though you write some high level language in some sense, but the assembly could be somewhat different from that, right? So that kind of thing can be identified through this dynamic instruction count. So if you see a lot of single precision instruction, even though you are not using any single precision, there is something wrong in the assembly line, right? So that kind of thing can be detected. Also, you may want to know how many cycles are used per line, right? So probably you have thousand line of the kernel, for example. It's not optimal, but in some community really enjoy writing very heavy kernels. So you have thousand line, and then you cannot see the all line by line base, right? So you may want to see what is the line use most of the cycles. So in that case, you can use basic block latency analysis. So you can identify the issues caused by the algorithmic inefficiency, and you can also measure the execution time of all block and identify which line spend most of the time, right? So for that, you can use the VTune GPU hotspot analysis with the additional knob with source analysis, and then it will provide this kind of information. So for each line, it will give you how much cycles are used by each line. So in this example, this line spans 4.3% of the entire cycle, and this line use 3.9% of the cycle, right? So you can identify which line spend most of the time. And then and then you can also you may be also curious about how much memory latency your code is using. So for that, you can use memory latency analysis using VTune GPU hotspot addition with the additional knob here, and you can also see the memory throughput bound. You can use it for the memory throughput bound application, and you can also identify the latency issues caused by memory access, and also provide the memory read synchronization instruction to understand your kernel execution time, right? So in this example, there is only one read line. This is very simple micro benchmark. So this line just spend most of the time, and then they are just sitting on the register, and then they don't use any memory latency. So this is kind of the expected way, right? So, but if you're, this is also useful to understand your memory access pattern and unexpected memory access pattern. You can minimize that using it by checking this information. Okay, and the last feature I would like to say is uh, people say, yeah, even though your system is exaflop or gigaflop, whatever, but most applications are memory bound, right? So in that case, a way to improve your application performance is to understand your memory access pattern and avoid any store region, right? So GPU Max GPU on Aurora, it provide a hardware assisted store sampling technology. So for that, you can use this additional knob, source analysis, and then store sampling analysis, and then it will give you this kind of the store ratio per line here. So this number is 42.7% time is the store, something like that. This is problematic node, right? And then you can expand these features per the store region. So there are 9 store region here. So this is percentage of GPU active, and this is some other region. This is control flow dependency. This is pipeline dependency, and this is send instruction. And this is also delays in the distributing accumulation of the instruction, and SBID is scoreboard mechanism to, for example, data hardshot and synchronization instruction, and also instruction patch the store region, right? So this kind of information you can see that, and then if you can find a way to improve, remove this source store region, you can get the better performance because you can minimize the memory store, right? So this is kind of, oh, one more. So another interesting thing is on Aurora node, we have 6 GPUs, and 6 GPUs are connected through the X-Link. And sometimes an application is supposed to use this X-Link for the GPU to GPU communication, right? Sometimes your application, GPU kernel application is good enough, but sometimes you may have too much synchronization between the GPU. So that may be the bottleneck. So to understand the XE traffic, you can also use GPU offload analysis, and then using additional knob here, analyze the XE link usage true. And you can understand the cross-card memory transfer and X-Link utilization, and also you can visualize the GPU topology on the right-hand side here, and then also you can see the X-Link usage and correlate with your code execution right here, timeline view here, right? So you can see this GPU stack 0 has a communication with another GPU stack here, and at this time it has communication here and here and here, right? So you may monitor this actually link traffic is reasonable or not. If not, you can also dig into um, um, the part of kernel for the GPU to GPU communication. So yeah, this is kind of overview, and I have more items, but any question about the features? Okay, so yeah, again, if you have any question, please put your question on the channel and the Zoom chat, or just mute and speak up. Okay, I can answer those questions. Okay, so another feature is the profiling your 1CCL workload using Pigeon Profiler. So 1CCL is communication layers used by the machine learning applications, right? So VTune APS and VTune HPC performance analysis provide a set of the 1CCL workload data. So APS provide time spent on CCL task and also percentage of the total time. And if you want to get the more details, you can run the HPC performance characterization analysis, and it provides 1CCL time and top 1CCL task and 1CCL communication task in summary window and the timeline view. So here, I think this is from the APS view, so you can see the APS, what is the top 5 CCL function, how much time used, how much less time by the CCL time. And I think this is HPC performance analysis view, so it shows CCL top 1 CCL task and how much time, how much call happen in this application, and this is kind of more detailed analysis. So I just provided several features available feature, not all the features, but some features commonly used on Aurora. And once you do that, most frequent question or complaint about VTune is, oh, VTune overhead is a little bit higher than expected, right? I'm saying very nicely now here. But again, after running that, the older question is, okay, we need to spend more time to collect VTune data, but sometimes it's too much, right? How to reduce that overhead, collection overhead? That's really a fair question because especially if you're running some real-time application and runtime is pretty high, right? So uh, we want to find out a way to minimize that overhead. So the first, there are several suggestions from the Intel, and I just want to share it with you. So first one is you may disable the stack collection. So stack collection sometimes it provides all the detailed stack from the OS level. Usually, we don't care what OS is doing. We don't care what low-level API is doing, right? So in that case, you may just disable stack collection. So stack collection spend a lot of resource on the CPU level, CPU side. So if you disable the stack collection, you can reduce significant of collection overhead. But if you want to see more detailed stack information, if you're very important, you have to use the stack information. Depending on the application or the framework, you need to use that. But in that case, you may not be able to do that. But in general, you may just want to look into the kernel level analysis without the detailed stack information. You can just force disable it, okay? And the second one is VTune collect all the hardware sampling data. So the default sampling frequency is 1 millisecond on the GPU side. So what it means, if you don't do anything, you're collecting all the hardware sampling data per every millisecond, right? So, and also that is kind of determine size of the collected data, right? So if you want to reduce the overhead, you may think about increase the sampling interval from 1 millisecond to 5 millisecond, etc. Right? So now that means you can reduce the collected data size to 20% because instead of 1 millisecond, every 5 millisecond you collect data, right? But the problem is you also need to think about what is your user kernel execution time. So if you have pretty heavy kernels running maybe 10 millisecond, 20 millisecond, 100 millisecond, it's fine. You can reduce it to 5 millisecond, right? But if you have so many tiny kernels, every kernel is running, for example, zero point 0.5 millisecond or 2 millisecond, 3 millisecond, in that case, we don't recommend to reduce the sampling interval to save your time, right? And then that means you still collect some data, but that data is some kind of the statistical data. So it may not be directly relevant to your execution. So it may have some noise, right, in the collected mode. So in this case, you may need to consider what is your target kernel and kernel execution time, and then you need to adjust your sampling interval based on that, right? But again, depending on the case, the adjusting sampling interval is also kind of good way to reduce your overhead. Another thing is, in general, we have most of people use some legacy code written by more than 2 or 3 decades, right? So if you're a PhD student, postdoc, or some developer, you may just look into, okay, now I'm looking to this optimize this smooth kernel or some reaction kernel, whatever, right? So usually you just focus on specific kernels, not the every kernels. So in that case, you don't have to collect all the performance data from all different part of the application. Instead, you may just want to look into the specific kernel of interest, right? So in this case, you can use the computing task of interest and specify that kernel. That means VTune just disable other kernels collection. It just focus on that specific kernel. So that reduce a lot of overhead. So this is also useful information. And also you can, I just have the link from the Intel website. You can go into more details on this thing, okay? And another thing is that the selective profiling, for example, even on a single node, we have 12 MPI, 12 the GPU device, logical device, 12 types of GPU, right? So even on a single rank, we run 12 MPI rank. Maybe you just want to run, you just reduce the 1000 node case to four node case to profile that, right? And then 4 node case, you still use 48 MPI rank, right? So in that case, if you just and then if you think if you don't use a lot of different, if you think all NPI rank use a similar type of task, all right. On safety code, if I don't do the adaptive mesh refinement, I do. I think most of code, most of NPI rank has a similar size of the task and similar type of work is repeated, right? In this case, you don't have to monitor all the NPI rank or the memory device, right? So in this case, you can just specify a specific NPI rank of interest and then collect that NPI rank, and then you can reduce the collection overhead because you just focus on single NPI or single couple of NPI out of the 12, right? And then you can also reduce the finalization time because collected data size is smaller, and also you can reduce the storage overhead, right? So a way to use it is using MPMD mode, multi-program, multi-data mode, which means in this example, I'm running with the 24 MPI rank on 2 nodes, but I just attach VTune on the first rank. So MPI XCC and CPU bind, GPU tile compact, and then I just put the VTune collect GPU hotspot result and very first MPI rank 0. And then put the colon and NP23 without VTune, which means I'm running still 24 MPI rank on 2 node, but I'm just attaching VTune to very first MPI rank and other MPI rank running without the VTune. So you just focus on the first MPI rank. This is another way to reduce your collection overhead. This is a fancy way to using some script. So this is used as a hack example. So you have MPI line here, and then you have the bash here, and then you have export selected rank, and then specify here. So in this example, I'm using 12 MPI rank. So you may just say, oh, I think rank 5 and rank 10 is interesting. So you may just put on the 5 and 10 here, and here in the if statement on the bash, you can see the Pmax rank is the MPI rank provided by the PBS. So here using this one, if your MPI rank is equal to the selected rank, you just run with VTune. Otherwise, you just run the hack without VTune. So this is kind of the advanced expression using the NPMD mode. So either way, you can try it out. So this is kind of the naively collected data, how much time you can save. So with the hack example, one of my Intel engineer tried it out. So with single node, it takes 52 seconds without VTune. And then when he attached VTune to the one rank, it spent 1 million 4 seconds, so it's kind of 12 seconds more. But when you try collect everything, it takes 1 minute 24 seconds, so kind of 30 seconds more, right? When he run the VTune with the 4 node, application time is 36 seconds, and profiling one rank spend around 10 more seconds. But profiling all rank is 5 minutes 15 seconds. So more GPU, more node, and more data. So it takes more time. Storage overhead is on one node, one rank profiling 20 to 50 megabytes, and all profiling around 300 megabytes. 4 node, one rank, 360 megabytes versus 400 megabytes, right? It's not very significant in the storage overhead, but at least the execution time is pretty significant. And he also tried even with the finalization. Finalization is not required on the compute node, but he just included it in it, and then it is much more time used on with the all rank execution, right? And then much more storage overhead. And another way is instead of specifying the MPI rank, you may just want to look into specific GPU, right? For example, I'm running 4 nodes, and then maybe per node, there may be some difference between the cases, right? So instead of specifying NPI rank, you may just say, oh, I just want to look into the second GPU card activity. And then in that case, you can just use a target GPU knob. So you can do the VTune help collect GPU hotspot, and then it will provide all the BDF bus device function ID. So using that, you can just add GPU hotspot, knob, target GPU, and specific BDF number. In that case, what happens is on this every node, it's just between just looking into that specific GPU card. So without the specifying MPI rank, you can also see monitor the specific GPU card from your execution, right? So, and also this is kind of different from selective rank, but the kind of similar impact happen. And then combination of this MPI profiling, selective MPI rank, and the target GPU is recommended to minimize unnecessary data, right? So here, using the target GPU with a single GPU 1 minute and then all GPU 7 minutes, 2 GB, 2.6 GB. So depending on the situation, it may be very significant, it is not very significant, but you can keep in mind this is a viable option to reduce overhead. And another thing is also again the disabling program API collection on the GPU side. So it's kind of disabling core stack collection on GPU side. So depending on situation, you may say, I'm not interested in the stack collection, so you may just disable that, and then you can reduce the overhead using that. So yeah, this is about the general overview of how to reduce the overhead of the VTune. Any question? Okay, if not, let me move on. So another way is ITT API. ITT API is instrumentation tracing API. So you can instrumentation and tracing technology API, right? So you can control application performance overall based on amount of trace. So maybe even inside of the application, you may just interested in some specific spot of the application, not the kernel or yeah. So different granularity you may interested in, right? In this case, you can use ITT API. So you need to specify the LD library path for ITT API and then just use it. And then what you usually do is you can just specify ITT task begin and ITT task end, and you can also put the note for the name, right? So in this case, it's not a kernel level analysis. It just started the ITT analysis at that point, at beginning point, and then collect the mode, and then it just stop the collection at the ITT task end. This is kind of simple example for the C, and it also available in Fortran and Python. So this is a kind of Python code. In the Python to annotate Python code, it provide py PyITT API. So you can control application and mark up the Python code and also wrapper. and it's very useful in AI HPC applications. So um, and this is example. So here ITT resume start, and then using the torch autograd profiler emit ITT, then torch profiler range push training, which is kind of the name like training, and then the start kernel execution, and then torch profiler ITT range pop, and then ITT pod. So as an example, as a result, you can just collect the corresponding performance data only for this part. So it's available on C, C++, Fortran, and also Python. So you can use that to minimize it. Okay, and there's kind of yeah, up to now I explained what kind of features are available, what kind of what kind of tips we can use to minimize the collection overhead. And then I'm going to talk about how to see those data. So VTune provide a nice interface to see the data. So our recommended way is using VTune web server. So before you start, I ask you to include these three lines in your local laptop's SSH config file on your local system. The thing is that these three lines enable you can reuse your login credential to ALCF system. So once you establish the login to the Aurora and Polaris, and then if you do the access to Aurora class again, you reuse that credential and then get the same login node. So two benefit is you don't have to type your login credential at every terminal. This is one thing. One thing for the convenience. The second thing is once you establish the SSH to the specific login node, using this three line, you can access to the same login node for the next terminal. So that is the second one is very important for the web server because VTune web server is basically enable the SSH port forwarding on a specific login node. And then to enable that, you have to use the same terminal to use that, right? Same login node to use that. So otherwise, you have to grab this specific login node. You enable the VTune backend, and then you have to use the same login node. That is also possible, but this is more convenient way. So add the three lines in the SSH and config file, so I can show you on my case. So a lot of things I have, but I have a host alcfnl.gov and then control master and then control pass like this way, right? So I added that. And then open up the new terminal and then log into the Aurora login node. So I already established here. So before that, if I open up the terminal, I go the same login node here, 009. This is established 009, right? Okay. And then what I need to do is module load one API, but on the login node, we already have one API module here. So you can see one API module here. And then I will do VTune backend and data directory, and I will use Flare ALCF training. And then I created my own folder over there. So I just do that. Once you do that, you can see some HTTP address here, right? So you need to copy in here. So 127.0.0.1.461.159. If you do that, you will have a slightly different port number. And then I will open up another terminal here. And I will do the SSH-L and copy twice and JaeHyuk, my original login here, right? So now I established the SSH port forwarding. So here I do the VTune backend data directory and then SSH shell 127.0.0.1 and port number twice, and then username aurora.alcf.nl.gov, right? And then what you need to do is you need to open up the Firefox browser here. Oops. Sorry, my Firefox is dying. That okay here, Firefox driver, and then what you need to do is you copy HTTPS file here, entire file here, copy with the port number, and just put it up here, right? So if you do that, you can see warning, potential risk ahead, just advanced it, and then accept the risk control, and you can see here. On the left-hand side, you see a couple of the directory on the data folder. And then you may see some VTune result file. So here, if you open up, you can see some VTune GUI interface here popping up. Okay, it takes a little bit time, but one advantage of using VTune backend is, in my experience, VTune is kind of providing the progressive approach, which means you run some application with VTune and then you understand what's going on over there. And then you decide what is your next step on VTune analysis. For example, running the hotspot analysis, you may just want to know, oh, you identify this issue, and then you run it again for that specific kernel with some specific additional instruction code analysis, whatever, right? So in that case, you have a second VTune result, and then after that, you identify some issue, and then run it again with another knob with started execution, right? So I would say, I would like to say this is kind of progressive analysis. So in this process, you don't have to download all the VTune result folder on your local directory. Instead, you just establish this VTune backend process and then just click refresh your Firefox and see more data here, right? So again, it is loading some data from the VTune server. It takes some time, but in terms of latency, it's much better than X11 forwarding case. So it's pretty useful. So this is a way to see a VTune result on the result. And this is kind of the cheat sheet. So all the command line interface I showed in the VTune GPU offload analysis, hotspot analysis, and instruction count analysis, and basic block analysis, etc. So yeah, if you want to try it out, once Aurora compute node is back, probably next week, you can try it out. You can use this sheet as uh, for the instruction, and then you can try it out and see the video application. Okay. Okay, so this is kind of overview of VTune. Any question about VTune? Okay, hearing none. So let me move on to Advisor. Advisor is another Intel tool, which is also popular. As I presented, the VTune has a lot of different features, very different scope depending on the collection mode. Advisor is kind of an alternative way to understand your performance because Advisor just collect all possible data and then it provide some pre-processed data to users instead of providing cache miss or some instruction count. It just collect all the data and then provide some pre-configured data. So if you become familiar with Advisor is more useful because it just give you some snapshot of application with some abundance of data and give you some tips to improve your optimization. Sometimes it's wrong, sometimes it's useful, but it try to give you some advice. So uh, it is why I'm kind of the pop. I'm a big fan of the Advisor. So Advisor has several different features. Upload analysis, Advisor just designed upload strategy, and it was very useful at the beginning of Aurora development because we didn't have specific GPU yet. So in that case, Offload Advisor give us a pretty good idea how to upload our code to the Aurora system. Looper analysis is also a very popular feature to understand what is application performance under the memory bandwidth and compute, right? And then give us some feedback and some performance hint. And also on CPU side, vectorization optimization, thread prototyping, and build heterogeneous algorithm. This is kind of a very useful analysis. But in this talk, I just want to focus on the GPU loop analysis. So Uh, for folks who are not interested in, who are not familiar with the GPU loop analysis, loop analysis has two axes. X-axis is arithmetic intensity, which is ratio of the flop or byte ratio of your kernel, and y-axis is the flop rate. And then depending on, based on the measurement, it measures the flop count by byte transfer, and then it gives you several point. And advisor provides three different colors: red color, yellow color, and green color. Red color spend more than 10% of time. Yellow color is between 1% of 10% of time, and green color means less than 1% of time. So if you want to tackle in your application, you may focus on, you may start with the red color with the red color because those colors spend most of time. You can look into that and then go different, right? So and another thing is there are two types of loop. Plateau loop provide your compute peak based on your instruction level, and inclined loop provide your memory bandwidth depending on the memory hierarchy. So the lowest one is HBM bandwidth, second lowest one is L3 cache, and the highest inclined one is L1 cache level, something like that, right? So and then depending on the mesh hierarchy, cache hierarchy, and your kernel intensity, you can find out what is how you characterize your application, whether this is compute bound, memory bound, if it's memory bound, which layer of cache is bound, compute bound, which instruction level compute bound, right? So it's kind of a very intuitive way to understand your performance analysis, performance characteristic. Oh, okay. There was some first question. Can this simple program tool be used on any system with any multiprocessor Intel CPU and Intel GPU if available? I'm thinking local. Yeah, yeah. So yeah, yeah. Yes, he answered the question. So the one good thing is Intel requested some license, but a couple years ago they just removed all the license requirements. So you can freely download your Intel VTune Advisor on your local system and run your cases. Okay. Okay, so how to configure the Intel Advisor on Aurora? Again, it's analyzer, so part of one API module. So whenever you load a one API module, Advisor is in it. So there are two modes of running a roofline analysis. One is roofline collection mode, which means if you just run without MPI, you can just do the advisor collect roofline, profile GPU, and then execute. So in that case, advisor require two execution. The first execution is in order to collect your hardware metrics, it should run the survey analysis. And then after run that, advisor required to run your application again with the exactly same workload for the type trip count analysis. This is to count your instruction using the GTP module inside of the advisor. So basically, advisor requires two execution. But if you use collect roofline without MPI, this collect roofline automatically execute your application twice. So with this single line, your application will be executed twice, and then it will provide all the collected the data. But this mode is not available on MPI. So for the MPI execution, you have to run your application twice with survey analysis and trip count analysis. So this is kind of corresponding command line. So first line is it also uses NPMD mode. So in this case, I just attach advisor to first MPI rank out of 12 MPI ranks. So MPI run, GPU tile compact, advisor collect, survey analysis, GPU tile, profile GPU, and run execution. And then with other 11 MPI rank, I just run my application without advisor, right? So once it finishes, on the same folder, I run it again with the GPU trip count analysis and profile GPU and flop load trip count, and you do that, okay? So once you finish this survey analysis and the trip count analysis, you can generate the HTML report. So advisor report all, and then the report HTML file. So you can get this loopline underscore all HTML file, and then you can see that. So this is kind of overview of the HTML file. So you can see you can switch the data type on this tab and the customizable roofline chart here, and also performance of the computing task per kernel. It provides all useful data, GPU utilization and memory bandwidth, etc. And also, if you go to GPU detail, you can see all the different memory metrics pre-configured by the advisor. So I would like to give you the demo. So what I did was I put the data on the Aurora here. So you can go to Flare ALCF training. If you go there, you can see a lot of folder, but you can see the tools underscore Intel, right? So before moving on, I'm asking you to make mkdir and user. So in my case, I already created a JQuack module here. So create that and then go to the user here. And I will just move this one. I just tested here, right? So on here, I will just copy cp-all and Flare ALCF training and tools Intel to this folder. And then you can see tools Intel here, right? So once you copy this file to your local directory, you can see these files here. And then what I want to do is just make. Okay, I will just make. If I do the make, you can see the two executable. The first executable comp geoseries omp mpiccctp, right? So if you do run it, what happened? Nothing happened because we are on the login node. There is no GPU. There is no MPI execute available because we are on login node, right? So once Aurora system is back, you can just try it out. This example, right? So MPI run -12 GPU type compact, and then comp geoseries, and then 2048 10,000. It will show you some standard output. So just try it out once system is back. Now system is not available. Let me move on. So on compute node, what you can do is for the APS, on the APS example, you can just run MPI run GPU type compact APS R APS result, then run it, right? Once you're done, you can do that. VTune analysis, again, for GPU hotspot analysis, you can do that and just try it out. But this is an advisor analysis, you can do that, right? So, but unfortunately, we don't have a available compute node. We will just move on whatever we can do, right? So just copy. Once you copy the tools Intel on your local directory, you can see the APS result .tar.gg, right? So I will just untar APS result. So we have APS result. So if you run it on your compute node, you probably have some corresponding result file here, right? So what I want to do is APS report metric APS result. So APS report. Sorry, I don't have good memory. So metric and question mark and APS result. What it's showing is you already collected APS result, and then this CLI provide what kind of information is collected in your APS result folder. So it's saying MPI time, MPI hotspot, MPI com rank, size, whatever, disk IO, virtual memory, and this kind of information is collected, right? And then and then I just want to see some part of that. So I just want to see what is GPU stack utilization, maybe. Yeah, GPU stack utilization per device. So if I want to do APS report metrics and I'd like to say GPU stack utilization per device, copy. And then maybe OpenMP, I'm using OpenMP in this example, so maybe OpenMP upload time, where is it? Where is OpenMP upload time? Here. I'll just copy, paste, and then GPU accumulated time per device here. And then if you run it, sorry, and then APS result. Mm, yeah. If you run it, it will give you the standard output data for the what you requested, right? So in this example, I use a 12 ampere rank. So OpenMP time per rank is this amount of time. So from this case, you can see load imbalance on the OpenMP upload time, and also GPU accumulated time is here. So if you have some load imbalance issue, you can see very high device time here, right? And also GPU stack utilization. This is very simple benchmark. It's kind of 1.2% of the device time. But in general case, you may expect more than much higher than that, right? 50%, 60%, 70%, something like that. So this is kind of, I mean, APS result. And then you can also download this APS report that the HTML file on your local folder. I already downloaded it. So if you do that, you can just open it up on your Chrome folder. So you can see this kind of information here, right? So CPU, GPU, time, and if you hover your cursor across the number, it will give you also distribution here, right? So this kind of information. So HTML file will give you some summary overview, and then once you identify some specific counters, I mean specific information, you can go into the CLI information to get all the data from each node. So yep, this is a thing. And then the VTune example, you can also go to here. So if you copy the tools Intel, you already see the VTune result underscore GH I collected before. So GXDF. And if you untar that, you will have some order here, VTune result GH and X4015, this node. So what you need to do is you need to establish Firefox, right? So you can just follow the Btune backend instruction. Then here Btune result GH4015. So I will just open up. Yeah, it is popping up. Uh, it will take time, but yeah, I will give it some time and I will move on. Okay. So once you do that between backend, you can see that we will see together. And then another thing is advisory example. So again, if you go back to the tools Intel on the Flare system, you can see roofline underscore or HTML, right? So I already downloaded it. So if you open it up, you can see this folder. So this is kind of overview here. So CPU, GPU, CPU, GPU, and then what is hotspot. This is a single kernel execution, so you don't have much. And if you click the roofline vision, here there are three things, right? So I just click the CORM, L3, and HBM, so which means three different layers, CORM, the L3 layer and HBM layer. So you can see for single kernel, you can see the three different the dot based on the each hierarchy. So this is HBM, the L3 intensity is pretty high, which means it has very good cache locality, right? L3, so it's bound by the DP, right? And then it says the 27% utilization, which means you have chance to increase the performance much higher. And then COM data is very close to the register, so all the traffic's here. So in this example, what I need to do is if I somehow restructure the S3 cache access pattern, I can move this point to the right hand side and get better performance, right? So here it shows, once you click the corner, it will show you some corresponding number of integer operation, floating point operation, and the bandwidth, L3, HBM, and instruction mixes, everything, right? So basically, it is collecting same kind of data from the VTune, but it's kind of more pre-configured, processed data. So you don't see the raw data much, but you can see more process data here, right? So here the operating point operations and data transfer and kind of details here. What is SIMD width, and then COM data, L1, L2, SLM L3 here. So a lot of data is stabilized in the advisory report, and then GPU memory access pattern, utilization, active, store, idle, and the occupancy, exit instruction, etc. Right? So this kind of information is provided by the advisor, and also you may be able to find out what is the issue of the case, right? So this is kind of simple example, but I just want to give you more real application data here. So if you go to the REF folder on the Flare file system, I also tested AMR wind cases. So APS result, you can see CPU time, GPU time, MPI time, 40%, utilization 33%, etc. Right? So config layout is pretty similar, but the data is more real data. And also, if you open up the advisor report from AMR Wind, you can see the similar summary, but if you go to GPU region, you can see a lot of different kernel here, right? Because this is not a benchmark, this is real application. So you will have a lot of different kernels at the bottom here. And then even for the red part, if you extend it, depending on the kernel argument, you can see a lot of different cases here, right? Um, so So some users who are familiar with NVIDIA system, probably for reference model, they will use an Inside Compute tool, right? Inside Compute tool is very nice tool to understand the kernel level analysis, but the advisor has different approach. Advisor try to collect all the data across the applications, not just a specific kernel. You can do that, but by default. So you can give more process data across all the corners in the applications. While Inside Compute provide very specific the loop line data to the very specific kernel invocation. So it's kind of the different preference, right? So, but both of them basically provide all the required interesting data for based on the loop line. Okay. So let's go back to the VTune. So yeah, it's loaded now, and then you can go to graphics here. It's loading hierarchy view. Takes time. Okay, let's give you some time there. Okay, so this is kind of a login demo. So this demo on the login node, you can do it right now, right? And then once the system is back, compute node is available, you can try this demo on the compute node once the system is back. So just try it out, and if you have an issue, question, feel free to let me know through the Slack channel. So while we are waiting, we don't have enough time, so just 10 minutes. Let me move on to lightweight tool, Intel tools. So Analyzer is embedded in one API, but Intel also developed some lightweight tool because they also realized Analyzer is great, but it's pretty heavy. So they want to provide some lightweight tool. So Intel unitrace is one of the tool, and xpu-smi is another tool. Unitrace has very similar interface like iProf. The Thomas gave us a really, really nice talk in the morning. So iProf was developed very early stage of Aurora development, and then we use our iProf a lot because this is very intuitive and very lightweight, right? So Intel also developed a similar tool, so Unitrace. You can measure the application performance using tracing and profiling and host device activity, and provide level 0 host activity device kernel and or the profile layer MPI SQL CNN, CCL1 DNN, and also GPU kernel and profile hardware performance counter data as well. So you can just load the xpu-smi module and then do the unit trace. So again, the unit trace dash help give you all the different options here. And if you do the unit trace with the Chrome MPI logging, SQL MPI logging, and CCL MPI and CCL logging, you can see you can visualize that timeline view on the Chrome browser. So MPI activity and SQL activity and the Chrome CCL logging, right? So in order to use the unitrace, you can just load PTI GPU module and then unitrace version 212 is available. Unitrace the device list, you need to do that on this compute node because on login node you don't have any device. And unitrace metric list, you can see all the different hardware metrics available through the unitrace. And xpu-smi is XPU System Management Interface, and probably if you're familiar with NVIDIA system, you probably use NVIDIA SMI to see the real-time the device utilization, right? So xpu-smi, you can expect something similar on Intel GPU. So in order to use that, you can just load xpu-smi, and we have 1.2.39 version. And on the compute node, if you type xpu-smi discovery, you can see all the GPUs available, and then depending on the counters, you can also see the power, frequency, and utilization and memory traffic, something like that, right? So uh, what you can do is while you are running some application on a specific compute node, you can directly SSH to that specific node, right? So you're running 1000 node case, and then you probably have the compute node list from the job scheduler. You can see that. And then if you're curious whether your the first node or second node, what kind of activity is going on, you can just do the SSH to that specific compute node and then the load xpsmi and run the xpsmi dump and just reading power data or frequency data or utilization, etc. So you can easily find out without some specific profiler, you can identify you are actually using all the devices or some devices either or not. So this is kind of another live way to check your application performance. So for the demo, you can just load the PTI GPU. This is for the PTI GPU unit trace case once the system is back. So you can just do the npi run and then do that. And this is a XPSMI demo case, right? So this is all I have, and I think we have 7 minutes. Let's go back to the VTune case here. Okay, so once you click that, you can see the VTune graphics memory hierarchy diagram here. So you can see XC cores and vector engines, SLM, L3, and HBM cache, right? So what you can see here is it's either is very high, right? Because that hierarchy represents all the GPU 3 activity. So you can go into stack 0 and comp geo OpenMP upload. This is my GPU kernel. So if you click that, this diagram is loaded again based on this specific kernel. And then you can scroll to right to see the total time, how many invocation happen, data transfer happen, XPE array ratio. Now, here you can see the active rate is 67%, store rate is 18%, idle rate is 14%, occupancy 85%, AE active 1012, 53, 41%, right? And then you can also see the data traffic between L3 to the X3 core, 20 gigabyte read, 19 gigabyte write. And then from the L3 to HBM, 120 megabyte read, and then 12 megabyte write, right? So this kind of information you can see. And then if you go to platform here, it will give you the timeline view across the different GPUs, different activity. It will coming up. So while we are waiting, do you have any question? We just have 5 more minutes. Okay. So what were the x and y axis on graph that was shown earlier? X and y graph on the which one? Advisor data or which data? You mean here? Grouping. Okay. Here, x-axis is arithmetic intensity, which is the flop over byte ratio. So for example, if you have a kernel, your kernel probably requires some data from the memory, right? So for example, your kernel execution require 100 megabyte from memory, which means your memory traffic is 100 megabytes, right? And then using that 100 megabyte, you probably have some operations, right? It could be floating point operation, integer operation, whatever. So for example, 100 megabyte versus you have 100 megaplop happen on the kernel. In that case, 100 megabyte over 100 plop over 100 megabyte become the one, right? So that is kind of x-axis ratio. So which means if you have a lot of floating point operation per memory read, which means your intensity become higher, which means you're more compute bound because for the given amount of the data, you have a lot of floating point operations, which means very, very compute intensive, right? Or depending on the algorithm, you may have very little operation per read. You may read a lot of data and process a little bit and then read a lot of data and write a lot of data. In that case, you can say application is memory bound kernel and then your power by ratio become lower. So you become move on this one, right? So this is x-axis and y-axis is measured plot rate. So whether your application kernels running 1 gigabyte per second or one gigaplot per second, one teraplot per second, one exaplot per second, depending on your application workload, you may have some number of plops you can execute per time, per second, right? That is kind of power by ratio. So this is x-axis, power by ratio, y-axis, and plot rate. Does it make sense? Okay. Okay, back to the timeline view here. Okay, so here we can see the timeline view here. So x-axis is time and y-axis is this is kind of vector engine. This is a thread dispatcher. This is the memory occupancy. You can zoom in here, right? So then you can see more detailed data. So yeah, this GUI interfaces require a little bit of latency, but compared to X11 forwarding case, latency is much, much lower than before. So we highly recommend to use VTune backend mode to post-process your VTune data. So I think that's all I have. We still have 2 minutes, so if you have any question, feel free to unmute and ask questions.
I think there is like one or two on the chat, JaeHyuk. Or no, there is not.
Yeah, I just answered the questions. On the chat, mean the Slack?
No, they are not questions. I thought there is a question.
Okay, so yeah, maybe I introduced the 5 different tools in the 1.5 hour, right? So maybe this is too heavy. But if I just summarize, at scale, try to use APS tool to understand your performance characteristic at scale. And on node level analysis for progressive way, you may try to VTune analysis because it will give you some amount of data and then you can identify what's going on and you can decide the second step, third step. And if you want to see some kind of pre-configured the data for the performance and get some performance tip, you can just use advisor, reply feature. This is the way. And I'm kind of a big fan of the iProp, but if you see some some other information, other features, you can just try the unitrace and then real-time monitoring of your device. You can use xpu-smi using the SSH to the compute node directory, right? So there's kind of a quick 1 minute summary. I hope you can understand what kind of tools are available on Aurora from Intel, and I hope I don't confuse you too much. So if you have any further question or some use cases, we also very want to have some collaborate with you guys for the use cases. So if you have any use cases or any questions, feel free to ping me through the Slack so we can collaborate later. So it's 2 p.m. So I think I'm done. Thank you guys.